right, welcome back. Section 2.1, Measurement, a Common Language. Did you ever ask a relative for an old family recipe? If so, the answer might have been use just the right amount of flour and water, add a spoon of oil and a pinch of salt. Bake it for a while until it looks just right. Instructions like these would be difficult to follow. How much flour is just the right amount? How big is a spoonful or a pinch? It would be impossible for you to know what your relative had in mind. You could end up with disastrous results. All right, this is why we have a standard measurement system, especially in science. Okay, the recipe example illustrates the importance of using a standard system of measurement. This is especially true in science. Using the same system of measurement minimizes confusion among scientists all over the world. All right, we're going to talk about the metric system. The metric system is used almost all over the world except for in the United States. In science, we do use the metric system a lot because we can compare our results to scientists all over the world. So more than 200 years ago, most countries used their own measurement system. Sometimes two or more different systems were used in the same country. In the 1790s, scientists in France developed a universal system of measurement called the metric system. The metric system is a system of measurement based on the number 10. The International System of Units, SI, modern scientists use a version of the metric system called the International System of Units, abbreviated as SI. Scientists all over the world use SI units to measure length, volume, mass, density, temperature, and time. Using SI as the standard system of measurement allows scientists to compare data and communicate with each other about the results. In this book and others in the Science Explorer program, you will use both SI and other metric units. Figure 1 lists the prefixes used to name the most common SI units because they are based on multiples of 10. SI units are easy to use. Each unit is 10 times larger than the next smallest unit and 1/10 the size of the next largest unit. This is similar to our money system, in which a dime is worth 10 times more than a penny, but 1/10 as much as a dollar. Okay, SI units are based on multiples of what number? 10. We just talked about that. We can go back here to figure 1, and this shows you the common SI prefixes, and you can also use this when you're converting the different types of SI units. All right, let's talk about length. How far can you throw a softball? Can you judge by eye how far the ball travels? A better way to find out would be to measure the distance or length that the ball travels. Length is the distance from one point to another. In the case of your softball throw, it would be from the point where you release the ball to the point where it first hits the ground. Units of length. The base unit of length in the SI system is the meter. 1 meter is about the distance from the floor to a doorknob. A softball throw would be measured in meters. So would your height. Most students your age are between 1.5 and 2 meters tall. Notice that they're using meters and not feet. Currently in the United States, we usually use feet and inches, but as scientists, we use meters. Science and history, the measurement system. Like so much else in science, systems of measurements developed gradually over time in different parts of the world. Let's see if we can read this one. A simple balance. The ancient Egyptians developed the first known weighing instrument, a simple balance with the pointer. Later, they had been the first to standardize a measurement of length. The length, called a cubit, was originally defined as the distance between the elbow and the tip of the middle finger. Standard units of weight in 640 BC. Merchants in Middle East and Mediterranean used units of weight to be sure that they received the correct amount of gold and silver in trade and to check the purity of metal. A talent was about 25 kilograms and a mina was about 500 grams. The Lydians minted the first true coins to have standard weight and value. 200 BC, standard measurements. Shi Hong, the first emperor of China, set standards for weight, length, and volume. He also improved travel conditions by setting standards for the widths of roads and for the distance between chariot wheels. All right, we're going to come down here and finish reading about measurements in history. AD 789, standard units of length and weight. The foot of Charlemagne, emperor of most of Central Europe, was set as a standard unit of length. The standard unit of weight was a Kospofund, translated into Charlemagne's pound. In AD 1714, there was a thermometer. Gabriel Fahrenheit invented the thermometer, a temperature measurement device that relies on the expansion of mercury with heat. His name later came to be used as the name for the temperature scale. AD 1983, International Standards. The International Bureau of Weights and Measures in France defined a single set of standard units. Scientists throughout the world use these units in their work. The official kilogram measurement shown above is kept in a vacuum chamber. All right. To measure objects smaller than a meter, scientists use units called the centimeter or the millimeter. The prefix centi means 100th, while the prefix milli means 1,000th. 1 meter, then, is equal to 100 centimeters or 1,000 millimeters. The length of a typical sheet of loose leaf paper is about 28 centimeters, which is equal to 280 millimeters. What unit would you use to measure a long distance, such as the distance between two cities? For such measurements, scientists use a unit known as the kilometer. The prefix kilo means 1,000. There are 1,000 meters in a kilometer. If you were to draw a straight line between San Francisco and Boston, the line would measure about 4,300 kilometers. All right, measuring length. A very common tool used to measure length is a metric ruler. Notice this metric not in inches. As you see in figure 2, a metric ruler is divided into centimeters. So you can see they're divided into centimeters. Okay. A common tool used, the centimeter markings are the longer numbered 1, 2, 3, and so on. Each centimeter is then divided into 10 millimeters, which are marked by the shorter lines. To use a metric ruler, line one end of the object up exactly with the 0 mark. Be careful when you're doing this. This can lead to some confusion. Then read the number at the other end of the object. The shell of the turtle in figure 2.8 is 8.8 centimeters or 88 millimeters long. So 1 centimeter is divided into how many millimeters? Think about it. The answer should be 10 millimeters. All right, mass. Can you lift a bicycle with one finger? Probably not, unless the bicycle's frame is made of titanium, a strong but very light metal. Most bicycles racers use titanium frames because the bike's low mass allows them to ride faster. Mass is a measure of the amount of matter an object contains. Units of mass. The basic unit of mass in the SI system is the kilogram. The kilogram is a useful unit when measuring the mass of objects such as bicycles, cars, or people. The mass of a wooden baseball is about 1 kilogram. To measure the mass of smaller objects, you would use a unit known as gram. As you can guess, there are 1,000 grams in a kilogram. A large paperclip has a mass of about 1 gram. Even smaller masses are measured in milligrams. There are about 1,000 milligrams in 1 gram. Measuring mass. To find the mass of an object, you may use a balance like the one in figure 3. The balance known as a triple beam balance works by comparing the mass of the object you are measuring to a known mass. When you use a triple beam balance, you first place the object on the pan. You then shift the riders of the beam until they balance the mass of the object. You can find step-by-step instructions for use of a triple beam balance in Appendix C, which we do not have. So let's see if we can find this. Okay, so this is our triple beam balance. So see where they put the turtle? That's where you would put your object you want to weigh. And then these riders, you would move back and forth until this pointer is right at 0 and is balanced. Then you read the riders, and you can tell how much the turtle would weigh. Okay? What's the difference between mass and weight? Mass is often confused with weight, but weight is not the same thing as mass. Weight is a measure of the force of gravity acting on an object. As you probably know, you can measure an object's weight using a scale. When you stand on a scale, gravity pulls you downward, compressing springs inside the scale. The more you weigh, the more the springs compress and the higher the reading. If, however, you were to weigh yourself on the moon, you would obtain a very different reading because the force of the gravity is much weaker on the moon than on the Earth. The spring inside the scale would compress much less. You would weigh less on the moon, but how would your mass compare? Because mass is the measure of the amount of matter an object contains. It remains constant wherever an object might be. Your mass on the moon is the same as your mass on Earth. You can see why scientists prefer to use mass rather than weight when making measurements. So for example, if I were to go to the moon, I might weigh less. So I would say, oh, that would be a good diet. But it really isn't, because my shape does not change. So my shape is my mass, because it's the amount of volume I take up. So my mass stays the same. I look the same, but my weight decreases because of the less gravitational pull on me. Okay. All right, I am going to stop here for the end of section 1. I will pick back up in part 2 of this video, and we will talk about volume.